All right, let's look at the other side of state machines. We've done analysis. You did analysis in your homework for, which says here's a circuit for a state machine. Tell me what it does. Okay, the other direction is I want a machine that does X. What should the circuit look like? So synthesis. So typically we start with a state diagram, something that describes how we move from state to state, and we want to come up with a circuit to implement this. So let me just make kind of a random state diagram. We'll start with let's just do two states. Okay, and I'll call this state 0s, and I'll call this state 1. And let's suppose that in this state we output a 0, and in this state we output a 1. So it's a Moore machine. And we're going to have one input, which is called X. And if we're in state 0 and we input a 1, we should move to state 1. And if we're in state 0 and we input a 0, we should stay in state 0. And if we're in state 1 and we input a 0, we should stay in state 1. And if we're in state 1 and we input a 1, I'll say let's go back to state 0. Okay, where does this diagram come from? Somebody gives this to you, or somebody describes a problem and you come up with this. Okay? So this is a starting point, and everything we're going to do is about how do we go from this kind of description to an actual circuit. But coming up with this description is a problem in itself. So a typical example would be, okay, I want to build an elevator control circuit. So what's the state of the elevator? Well, it could be on the first floor, the second floor, or the third floor. Or it could be moving from the first to the second, or from the second to the third, or from the third down to the second, or from the second down to the first. Okay? And depending on what state you're in and what button has been pressed, you're going to do something. If you're moving from the second floor to the first and somebody on the third floor presses the button, you want to continue from the second to the first, right? And then maybe you want to move from the first to the second, and then from the second to the third. So you would design a diagram, right? You'd figure out what your total set of states is, and you would have a set of inputs, which might be all the buttons, and then you would make this diagram saying, if you're in this state and this is the combination of button states, what do I want to do? What state should I go to? So for now, and for most of this chapter, right, we're going to start with a diagram, okay, something that's been given to us. And from here, we have to do the following. So we know that we have two states, so how many flip-flops do we need? So we have to answer this question. And there's different answers. We know we need at least one flip-flop to do any memory. And if we have one flip-flop, we can represent two things. So we could use a flip-flop that's 0 for this state and 1 for this state. Wow, we're getting really good hail outside right now. This has been a good spring for hailstorms. So 0 gives us this state and a 1 gives us this state. Or, you know, we could use a flip-flop and say a 1 means state 0 and a 0 means state 1. That's perfectly valid too. So we can do whatever we want. We could also use two flip-flops. And we could say our flip-flops will be 1, 0 for this state and 0, 1 for that state. That's perfectly valid too. So you have to decide what kind of association you want between your flip-flops and your states. So I'm just going to do one flip-flop, and I'm going to make a little state table. There's a kid in the hallway who apparently does not approve of hailstorms, because they are screaming. So my flip-flop is going to have a Q output, and I'll just call it Q instead of Q0. and I'm going to go into a state. Well, my flip-flop will output a 0 or a 1. What state do I mean when my flip-flop is 0? Could be S0, could be S1. I'm just going to call this S0 because it's less likely that I'll get confused. But you know, sometimes your states are called A, B, C, D. Sometimes your states are called running, stopped, or paused, right? And so we make a table that says what are the values for the flip-flop outputs that correspond to each state. Okay, and somewhere around here we have to address the question, what kind of flip-flops do we want to use? And it may be totally up to you, and if it's totally up to you, there's a chance you're just going to use D flip-flops, because D flip-flops are so nice to work with, right? Put in a 0, click the clock, flip-flop goes to a 0. Put in a 1, tick the clock, flip-flop goes to a 1. But for other reasons, there may be other kinds of flip-flops that we would want to use. So for a first case, let's just do a D flip-flop. All right, so next thing we're going to do is make a state transition table. And I'm going to make that using this diagram. So I'm going to start this on a different sheet of paper. Now there's one input to this system, okay, which I'm just going to call this input X. So let's say state, our output Z, and our input X. Okay, so let's make a state transition table. So we're going to have an input X. We're going to have a present state. Which I'm going to call S0 or S1. But then we're going to match that to a value for our flip-flop. Okay, so this is going to translate to a value for Q. So let me just do this much of the table first. And I'm going to fill in this Q column using this state table. If state S0 is sorry, I should have called these S0, S1. Right, those are our actual state names. Okay, so state S0 is the state we mean when Q is equal to 0. S1 is the state when Q is equal to 1. So this is kind of a, you know, intermediate column. This is really what we're going to work with, okay? But this is helping me translate from this diagram to, you know, ones and zeros. All right, well, if our input is 0 and we're in state S0, what do we want? We want our output to be a 0. In fact, anytime we're in state S0, we want our output to be a 0. And anytime we're in state S1, we want our output to be a 1. Okay, let's fill in our next state. If we're in state S0 and our input is a 0, our next state should still be S0. So S0, input is 0, next state should be S0. If we're in S0 and our input is 1, our new state is S1. So S0, input is 1, new state should be S1. S1 and input is 0, your new state should still be S1. And S1 with an input of 1, S1 with an input of 1, your new state should be S0. So S1, input 1, S0. Okay, so now I know my new state after the clock tick should be this. I can fill in what the new value of Q should be after the clock tick. And again, S0 means Q should be 0. And S1 means Q should be 1. Okay, so here we've got a table that completely describes everything from this diagram. But we're back to a truth table, okay? We're moving back to the beginning of the course now. So we could write equations for z in terms of x and q, right? So from this, we could say z is equal to what? X bar ANDed with q. I can write that neater. X bar ANDed with q, or x ANDed with q. And if we simplify that, we're going to see z is just equal to q. Which we kind of knew from here anyway, because z is 1 when you're in state 1, 0 when you're in state 0, while q is 1 when you're in state 1, 0 when you're in state 0. So by looking at this, we probably could have said, you know, z is just equal to q. But, you know, this is a methodical approach that will always work, even if there's no pattern that we can see. Okay, so let's figure out this business. This is telling us what we want Q to do after the clock tick. Okay, and we're using D flip-flops. So the behavior of a flip-flop is determined by the D input. In this first row, we're saying when the clock ticks, we want Q to change to a 0. Well, the only thing you can do with a D flip-flop, if you want it to be 0 after a clock tick, is set your D input to 0. Here we want the flip-flop to be a 1 after the clock tick, so set D equal to 1. And same here, and here we want D to be a 0. And we can write equations for D now as a sum of products. D is going to be 1 when we have x is 0 and q is 1, or when x is 1 and q is 0. Alright, we'll come back to this page in a few minutes, but this is enough to sketch a circuit. So what does our circuit look like? We have a D flip-flop. It has a clock input, which is just fed from a clock. Right, some external signal. It has a Q output, and it also has a Q bar output, which we can take advantage of. And we have an input X coming into the system. And so Z is just equal to Q. So we can take this and we can send that to Z. That's the output of our system. And our D input should be coming from X bar ANDed with Q or X ANDed with Q bar. So I can take X and Q bar and AND those. And I can also take X and invert it and AND that with Q. And I can OR those together and feed that into D. And this should act now like this. Okay, put power on, start putting a pulse train into the clock, right? This is just coming from, you know, a 555 timer or something. And if I happen to be in state 0 and my input is 0, I will stay in state 0. And if I raise X to a 1, what's going to happen? I'm going to jump to state 1. And if I keep my input at 1, the next clock tick, I'll jump back to state 0. And my output will be toggling between 1 and 0, 1 and 0, 1 and 0. And when I bring X back to 0, whatever state I happen to be in, I will stay in that state. So this is a circuit that will toggle my output every other time the clock ticks, as long as my input's 1. And when my input is 0, the output will just be stable. Okay, and by the way, this is also an exclusive OR. So if I notice that, instead of using 2 AND gates, an inverter, and an OR gate, I could simply take X and Q, put them through an XOR, and feed that back into D. Okay, but that's just, you know, a first half engineering 250 question. How do we write a equation to achieve this behavior of D, you know, based on X and Q. And we can do a sum of products. We wouldn't be able to simplify it with a K-map, but we could throw in an XOR here. Here, if I had done a K-map, this would have simplified down to Q. I just did it by eyeballing it. But you know, that's all the stuff that we've been doing in the first half of the course. This is where it all comes into play, is in, you know, in this case, actually coming up with circuits to achieve this desired behavior. Okay, so that's how we could implement this state diagram using a D flip-flop. But suppose instead that we had a toggle flip-flop. Suppose we were told we wanted to use a T flip-flop. All of this is still going to be the same, right? I'm going to start with a diagram. I'm going to look at input, present state, what the value of Q is for that state, what the output should be, what the new state should be, what the new value of Q should be. That has nothing to do with what kind of flip-flop I'm using. So if someone hands me the same problem and says use a T flip-flop instead of a D, all of this is still good. The only thing that changes is this last column. Now I need to think about a T flip-flop. Alright, my output's still going to be the same, that's just going to be Q. But let's look at T flip-flops. So a T flip-flop, remember, looks like this. And it has the following behavior. Right? If T is 0, my new value is the same as the old. If T is 1, my new value is the opposite of the old. It toggles. Alright, so using that idea, let's fill in what we want the T input to be for each of these 4 rows. So let's just look at the first row. Right? The current value of the flip-flop is 0, and after the clock tick, we still want the value of the flip-flop to be 0. We do not want it to toggle. So in this case, we should set our toggle input to 0. Okay, second row. The current value of the flip-flop is 1, and after the clock ticks, we want it to still be 1. We still don't want the flip-flop to toggle. So our T input should be 0 here. Okay, third row. Current value of the flip-flop is 0. After the clock tick, we want it to become a 1. We do want it to toggle after the clock tick. So we'll make the T input a 1, because then the new value of Q will be the opposite of the old. So in this third row, the current value of Q is 0. We want it to become a 1. We do that by saying set the toggle input to 1. So that when the next clock tick comes in, the T flip-flop will switch from a 0 to a 1. And then the last row, current flip-flop value is 1. We want it to become a 0. That's another toggle condition. So again, we want it to toggle. So if we were building this with a T flip-flop instead of a D flip-flop, what's our equation for T? Well, it should be X ANDed with Q bar, or X ANDed with Q. And put that in a K-map, you'll have a 1x2 rectangle you can cover. This turns out to just be X, right? X is 0, 0, T is 0, 0, X is 1, 1, T is 1, 1. So our simpler equation for the T input is just X. So this is what it looked like with a D flip-flop. With a T flip-flop, it's a little simpler. Right? There's our whole state machine. And go back to our original diagram now and think, does this make sense? Our original diagram said if our input was 0, our output should be unchanged. If our input is 1, our output should toggle every time the clock ticks. Well, that's what this circuit does. If our input is 0, our output's going to stay whatever it is. Could be a 0, could be a 1, but it's not going to change. But as soon as we set this input to 1, every time the clock ticks, this will change value. That's what this diagram is describing. So if you come across this example in a book, right, you'd be tempted to think, so why is this a T flip-flop, right? Don't try to figure things out like that. Come back to the systematic analysis, right? Think about this, figure out how many flip-flops you need. If you're going to use T flip-flops, fine, make a state assignment table and start filling in present state, output, next state, how should we set the inputs to the flip-flops. And miraculously, this is what pops out, right? And from that point of the journey, you can start to look back and say, okay, so why is this the thing that corresponds to that, right? And try to find meaning in it. But all of these problems, right, are done by doing this very systematic, very procedural, algorithmic process, okay? So if you know how to do this, you can take any of these diagrams and come back and work your way through it. All right, let me just mention something that you'll see in the book, and I don't want you to get tripped up on it, but it's not necessary, okay? But you're going to encounter this and you're going to try to figure out how this fits in. So let me talk about this. What were we doing to fill this in? I was going through a long, wordy analysis. If my current flip-flop value is a 0 and I want it to stay a 0, I'll set my T input to 0. If my current flip-flop value is a 0 and I want it to become a 1, I'll set my T input to 1. If my current value is a 1 and I want it to become a 0, again, I'll set my T input to 1. Okay? So you'll see tables for this in the textbook. And here's what these tables are basically saying. If you have a T flip-flop, so let's just go back to a plain old T flip-flop. Right, this is the table that describes the behavior of a flip-flop. We can write a different form of this, which says, suppose I have a current value of Q and I want a next value of Q plus, what should I set my T input to? So we can write a table with 4 rows that basically captures the thought process that we use to fill this in. Suppose my flip-flop is a 0 and I want its new value to still be 0. Set your toggle input to 0. Suppose the value is 0 and I want it to become a 1. Set your T input to 1. If it's a 1 and I want it to become a 0, set your T input to 1. And if it's a 1 and I want it to stay a 1, set my T input to 0. Okay? This looks very different from this, but it captures the same information. It's another one of these things we could call a dual. Okay? It's a different way of looking at this information. But you don't need this table. If you know what a T flip-flop does, and you know that your flip-flop is a 1 and you want it to become a 0, you just look at it and say, oh, I want it to flip, so I'll set my T input to a 1. That's all that one is telling you. Okay, so you look in the book, it'll talk about characteristic equations and excitation equations. That's what it's talking about. But concentrate on what these flip-flops do, how the outputs change in response to the inputs, and you'll always be able to fill in the input columns. Okay, and for D, it's totally straightforward. Set your D input to what you want the next state to be. For T's, it's a little more complex. If your new state is the same as the old, set T to 0. If your new state is different from your old, set T to 1. Okay, let me make another example circuit, and then we'll talk about JKs, but I want a more interesting circuit to talk about the JK case. So let's make a machine with 4 states. Let's make a machine with, yeah, let's do 4 states. And let's make a counter. So let's output 0, 0, 0, 1, 1, 0, 1, 1. And I'll put a key over here. So here's a state. Here's our output Z1, Z0. And I'll have an input. I'll just call it X. Okay. So here's the idea. If my input is 1, I'm going to go from state A to state B. And if my input is 1, I'll go from B to C. And if my input is 1, I'll go from C to D. And if it's still 1, I'll go from D to A. But if my input is 0, I'm going to count backwards. So I'll go from A to D to C to B and back to A. So this is called an up-down counter. So how many flip-flops do we need? 2 will suffice. Because 2 flip-flops, we have 4 possible combinations. So let's set this up with 2 flip-flops. And we'll start with D flip-flops because they're the easier one to work with. And I'm going to represent my 4 states like this. So I'll call my flip-flop outputs Q1, Q0. And I'll just use this pattern of flip-flop values for each of these 4 states. And I chose these carefully because, what's the output in state C? 1, 0. Well, that's the value of Q1, Q0 in state C. And what's the output supposed to be in state D? 1, 1. Well, that's the value of Q1, Q0 I chose for state D. So my outputs are going to be really easy. They're just going to be Q1 and Q0. Okay? So let's make a state transition table for this, and then let's look at different types of flip-flops. So let me do my input X, and let me do present state, and let me do Q1, Q0, and let me do my outputs Z1, Z0. So my present state can be A, B, C, or D, with inputs being 0 or inputs being 1. And the order I list these in doesn't really matter. Okay? It's a truth table, so technically you can list the inputs in any combination that you want. But I've done them in kind of the canonical ordering for my input and my cues. Right, so I've just filled in what each of these states A, B, C, D means in terms of flip-flop values. Let me put my horizontal lines here so we keep things neater. Alright, so what are the outputs? Well, as we already noted, the output is exactly the same as Q1, Q0. State A, the output should be 0, 0. So this should be 0, 0, 0, 0. State B, the output is 0, 1, and so on. So the output equations are as simple as you can get. And that's just because of the way I chose to set up my states. But let's look at the next state. Alright, if our input is 0, if we're in state A, our next state is D. If we're in state B, our next state is A. If we're in state C, our next state is B. And if we're in state D, our next state should be C. Okay, that's all for input equals 0, so following these 0 arrows. If our input is 1 and we're in state A, our next state is B. If we're in B, our next state is C. If we're in C, our next state is D. And if we're in D, our next state is A. You gotta ask questions if any of this is not making sense, right? Because we got another half hour of this. And I'm just gonna keep going, and if you're lost, then this is just gonna get more confusing. So if any of this is not making sense, you know, up to and including what is a state machine, let's talk about it now. And we got plenty of time to go through all of this, you know, next Tuesday. But is this making sense so far?
So far, so good.
Okay. This is something I haven't figured out with online classes, because in person, right, I can get a pretty good read from people, right, from their focus, if they're following this, if they're frustrated, if they're lost, if they're distracted, if they're bored, and so on. I don't get that online, right? So I'm kind of leaving it up to everybody here to either raise your hand or send a message in chat, or just turn on your mic and say, hey, what are we doing? All right, so continue with our state table. Let's fill in what we want the new values of Q1 and Q0 to be. And, you know, our table tells us if we want our new state to be D, then Q1 and Q0 should both be 1s. So here we should have a pair of 1s, here we should have a pair of 1s. If your new state should be C, then your output should be, your flip-flop should be 1, 0. If your new state should be B, your flip-flop should be 0, 1. And A should be 0, 0. And comment, this is basically just synthesis backwards, analysis backwards. Yes, that's exactly what it is. It's the exact thing that we did to analyze a piece of circuitry and get a state diagram. We're just running the steps in reverse, right? Which is why I say, A, if you understand analysis, then it makes it easier to do synthesis. And 2, as we do synthesis, your understanding of analysis will get sharper, okay? Because it's really the same thing, just going in a different direction. All right, so let's suppose we have D flip-flops. So we have D1 and D0. D flip-flops, easier of all the possibilities, because if we want Q1 to be a 1, set D1 to be a 1. If we want Q1 to be a 0, set D1 to 0. So for D flip-flops, we set the D inputs to whatever we want the Q outputs to be. And then we just write equations for D1 equals in terms of X, Q1, and Q0. And equations for D0 equals in terms of X, Q1, and Q0. And that's a truth table to equation proposition, right? So D1 is X bar, Q1 bar, Q0 bar, or X bar, Q1, Q0, or X, Q1 bar, Q0, or X, Q1, Q0 bar. And toss it into a K-map, simplify it, write an equation, D1 equals, you know, some function of X, Q1, Q0. D0 is some other function of X, Q1, Q0. And then sketch a circuit for that. Take these three things, run it through your logic to generate D0 and D1, feed those to the inputs of your flip-flop, and you're done. Alright, toggle flip-flops. Let's do this again just for practice. So I want to toggle, I want to set Q1, and here is the previous value of Q1, and here's the new value I want. Okay, so I just have to say, should I toggle this or not? So 0 should become a 1, yeah, toggle. 0 should become a 0, don't toggle. 1 should become a 0, toggle. 1 should become a 1, don't toggle. 0 should go to 0, don't toggle. 0 to 1, toggle. 1 to 1, don't toggle. 1 to 0, toggle. And this is a pretty succinct equation when you put it in the K-map. It'll come out a little simpler than the D1 input. Okay, T0, I'm looking at Q0 and Q0 plus. I'm going from a 0 to a 1, toggle. Going from 1 to a 0, toggle. 0 to 1, toggle. 1 to 0, toggle. 0 to 1, 1 to 0, 0 to 1, 1 to 0. Guess what? My equation for T0 is really simple. I just tie it to 5 volts. Okay, and T1 is some function of X, Q1, and Q0. Alright, let's look at JK flip-flops. So JK flip-flops are sometimes more complex. Why? Because each flip-flop has 2 inputs. So let me draw a picture. There's J and K, there's our clock, and we have Q and Q bar on the output. And remember how this acts. If J and K are both 0, the flip-flop does not change. If your inputs are 0, 1, the flip-flop goes to 0, 1, 0 goes to 1, and then 1, 1 acts like a toggle. Okay, this is going to make our life easier in the end. Even though we've got 2 inputs per flip-flop to deal with, we're going to get a lot of don't cares. Okay, so let's see how this works. So let's make a column for J1, K1. And then we'll do J0, K0 separately. Alright, so look at the first row. My flip-flop output is a 0. I want it to become a 1. Okay, so Q is equal to 0, and we want Q plus to be equal to 1. Well, how do I make that happen? I can force my output to be a 1 by setting J equal to 1 and K equal to 0. Right? Guarantee if J is a 1 and K is a 0, my new value on my flip-flop is going to be 1. But there's another way that I can make the output 1. Does anybody see what that way would be?
1, 1.
1, 1, why?
It toggles.
Because 1, 1 toggles. If my inputs are 1, 1, it says my new output will be the opposite of my old. While my old output is 0, when it toggles, it'll be a 1. So I could also do a 1, 1. So there's 2 possibilities for setting J and K to get this behavior. 1, 0 or 1, 1. So I'm going to combine those, and I'm going to say J has to be a 1, but K, I don't care what it is. Make it a 1 or a 0 makes no difference to me. And we really like don't cares and truth tables, right? Why? Because they give us dashes, and dashes you can choose to cover or not cover in your K-map. They never hurt you, but a lot of times they help you. So the more don't cares, the better. And any time that I'm going from a 0 to a 1, I'm going to say 1 dash. Okay, so here's a case where I've got a 0 and I want to go to a 1. That's going to be a 1 and a dash. Okay, let's look at the second case. I've got a 0 and I want to have the new value be a 0. So one possibility is 0, 1, because that forces the output to a 0. The other possibility is just 0, 0, because that says don't change. it's a 0. If I don't change it, it's going to stay a 0. So I could do a 0, 0 or a 0, 1. So again, set the j equal to 0 and the k value doesn't matter. So that's a 0 and a don't care. In any case where I have a 0 and I want it to become a 0, I can set that to say set j to 0, k to don't care. Alright, currently a 1, want the new value to be a 0. Well, there's two possibilities. Put in a 0, 1, right, because that forces the output to a 0. Or again, use a toggle. A 1, 1 will change this 1 to a 0. So combine those. First input doesn't matter. Second input should be a 1. So this is a don't care followed by a 1. And a 1, 0, 1, 0, that's a don't care followed by a 1. In our last case, currently output is a 1. We want the output to stay a 1. Two possibilities. 1, put in a 1, 0, which forces the output to a 1. Or 2, put in a 0, 0, which leaves the output unchanged. So 1, 0 or 0, 0. And that translates to a don't care followed by a 0. So j is a dash and k is a 0. And our other case where we had a 1 and a 1, that's a don't care and a 0. So we've got don't cares. Don't cares are nice. Okay, this is a case where this input excitation equation or table might be helpful. Okay, let's make a table for this. Current value of Q, next value of Q. What should we set J and K to? Well, if our current value is a 0 and we want the next value to be a 0, like in this second row, set J to 0, set K to don't care. Okay, current value is 0, we want the new value to be a 1, set J to 1 and K to don't care. Currently at a 1, want the new value to be 0, set your inputs to don't care and 1. And currently a 1, still want to stay a 1, set your inputs to don't care and 0. So this is just summarizing this thinking that we were doing in figuring out the J and K values for these different situations. Okay, so this is nice to have on your note sheets, but it's nicer to understand where this comes from, right? It's more efficient to have it written down, but make sure you understand the logic that we did to get these, right? If we've got a 0 and we want to come to a 1, we can either set the flip-flop or toggle a flip-flop. So a 1, 0 or a 1, 1 will both work. So a 1 followed by anything on K. So that's where that 1 dash comes from, for example. Okay, so we can fill in, similarly, J0 and K0 by looking at Q0 and Q0 plus. So a 0, 1 is a 1 and a don't care. And here's another 0, 1, so that's a 1 and a don't care. And here's a 0, 1, and here's a 0, 1. And a 1, 0, right, we want to go from a 1 to a 0, that's a don't care and a 1. So this is a don't care and a 1, and 1 to 0 is a dash 1, 1 to 0 is a dash 1, 1 to 0 is a dash 1. All right, so let's K-map these. Let's compare them. So let's look at the D inputs. Okay, so D1. All right. Alright, so I'll do X and Q1 and Q0, and I'll fill in D1. So it looks like 1, 0, 0, 1, and then 0, 1, 1, 0. Okay, and that's not going to cover very well. Okay, but it is an XOR type operation. So D1 is going to be X XORed with Q1, XORed with Q0, with a bar on top of all of it. That does not come out of the K-map directly. You have to play with XORs and recognize that. But 3 inputs, when you get this kind of pattern, 1, 0, 0, 1, 0, 1, 1, 0, that's an exclusive NOR of the 3 inputs. If it's 0, 1, 1, 0, 1, 0, 0, 1, that's just the straight XOR. Okay, but we could write this as a sum of products. It would be 4 product terms, each with 3 input variables, and all 4 of those sums together. So D1 is kind of complex. D0, 1, 0, 1, 0, 1, 0, 1, 0. I don't need a K-map for that. I see an alternating pattern here. Well, I'll do a K-map anyway. Alright, so D0 is 1, 0, 1, 0, and then 1, 0, 1, 0. And so this has a nice 2x2 cover, which says X doesn't matter, Q1 does not matter, Q0 has to be a 0. So D0 is just Q0 bar. And if you look at that, that kind of makes sense. D0 is just the opposite of what's in the Q0 column. All right. T0 turned out to just be 1, so that's about the simplest equation you could hope to end up with. Let's look at T1. And if nothing else, you know, these problems are really good at practice for getting better with K-maps. And I'm feeling the time crunch here, so my boxes are getting sloppier, but you know, if you're doing this with plenty of time, be very methodical about it. Okay, so T1, let's fill this in. So 1, 0, 1, 0. 0, 1, 0, 1. And I'm using my pattern that I know because I've written these before, okay? But you know, do whatever you have to do to fill these in. This has a nice cover. So this is X ANDed with Q0. And this is X bar ANDed with Q1 doesn't matter, but Q0 is a 0. So X Q0 or X bar Q0 bar. Alright, and then let's just do the K-maps for J1, K1. J0, K0, and I won't break these down to equations, but let's just do the coverings. So we'll do J1, K1, J0, K0. Okay. J1 looks like a 1, a 0, a don't care, a don't care, a 0, a 1, a don't care, and a don't care. K1 looks like don't care, don't care, 1, 0, don't care, 0, 1. J0 is a 1, a don't care, a 1, and a don't care, a 1, and a don't care, a 1, and a don't care. And K0 is a don't care 1, don't care 1, don't care 1, don't care 1. Alright, so these will get 1 by 2 covers. These will get 1 by 2 covers. This one we can cover the whole thing. We can set J0 equal to 1 and K0 equal to 1. We can just tie those to 5 volts through a resistor. And we're all set. And J1 is going to be something like X ended with Q0. And K1 is going to be, X bar ended with Q0 bar. And K1 is going to be X ended with, it's going to be exactly the same thing. Right? So a pair of relatively simple sum of products, 2 lines tied to 5 volts. That's the basic process for any starting state diagram, right? Decide how many flip-flops you're going to use, or you might be told. Decide what kind of flip-flops you're going to use, or you might be told. Make a state assignment diagram, and then build this state transition table from the diagram. And then figure out what your flip-flop inputs need to be to make all of this happen. To make it so that in this case you change from that value to that, and from this value to this. Set up your inputs, find equations, simplify, and then you can sketch your circuit. And in general, your circuit's going to look like this. So let's say I was using JK flip-flops. The clocks are always going to be tied together. Remember, flip-flops, you always have the true and the complemented outputs available. So we don't need a lot of inverters. And we have some input X. Well, all of this is going to go into some kind of combinational logic, which is going to implement, these equations for JK flip-flops, for example, and also generate, outputs. I switched to 1 and 2 instead of 0 and 1, sorry. But then, outputs of this are going to feed into your J and K inputs. Right, so that's our starting picture of a state machine from last week. Logic, right, this is your state memory. Combinational logic, which takes your current state and changes it into inputs to the flip-flops to set your next state. And then some combination of your input and your current state is used to generate your outputs. So the basic diagram, right, memory, combinational logic, right, that's your basic state machine. Inputs go into combinational logic, generate outputs, also generate the new state based on the current state. Alright, so take a look at the homework for Chapter 5, okay? This will let you do most of the problems in there. Take a look at the solved problems to get an idea what's being asked for, but don't try to just follow each step and mimic it, okay? Use the solutions to the solved problems to understand what it's asking. But when you actually try to design a circuit, right, try to do what we've been doing here, okay? Try to go through these steps and get this process down more and more. It will take a long time, okay? The first circuits that you do could easily take an hour or 2 to go through all of these steps, okay? But work methodically, systematically, and you will get there. All right, that's all I got. Work away on that. I'll get homework 4 graded sometime in the next few days and get some feedback back to you on that. And we'll talk more about synthesis on Tuesday, but try to get through as much of the homework as you can. I have office hours tomorrow at 8, and then Monday at 8, and then Tuesday at 8 and 11. So you've got, a couple of options, a few options to catch me before class on Tuesday. All right. All right, I will leave it there. Have a good rest of the day.